May I now invite Dr. Basak of Nuclear Fuel Cycle and Materials Section of Department of Nuclear Energy, International Atomic Energy Agency. And Dr. Basak is going to talk to us on Thorium fuel cycle applications, that program in International Atomic Energy Agency. Dr. Basak. Thank you. Cycle. I don't know. Perspectives. I don't know where is this. You just see here. This one. This one here. Yes. Thank you, Chairman. I thank the organizer for the invitation, and in fact, this gives me also an opportunity to interact with the participants here, particularly in the area of the activities related with the nuclear fuel cycle, or maybe specific to the thorium fuel cycle, so that we look forward to receiving more and more participations in the activities of nuclear fuel cycle that we have in the days ahead. I am also encouraged to see the participation of Dr. Kakutra here. He is always a source of inspiration for me wherever he is. And I have some special attachment with this thorium fuel cycle in the sense that we spent most of my professional career in my mother institute, Bhabha Atomic Research Center, in the development of thorium fuel cycle for our nuclear power program in India, apart from this other fuel cycle containing plutonium and uranium. So as a result of my special treatment, what I can present you today, the organizer has given you this source of thorium, the monazite, on display. I can give you this actual high-density thorium oxide pellets ready to use mode in our water-cooled reactors, in our these things, in the introductory side. How about this? Today, my focus of my presentation is in the area of this, what activities we have in the thorium fuel cycle in the agency. The International Atomic Energy Agency has many departments under the Director General. We have this Department of Technical Corporations, Department of Nuclear Energy, Department of Safety and Security, Department of Nuclear Science and Applications, Management, and Safeguards. And all these activities are related with these peaceful uses of nuclear energy. That's why we say IAEA atoms per peace. Now, I belong to the Nuclear Fuel Cycle and Materials section, which is a part of Nuclear Fuel and Waste Technology Division under the Department of Nuclear Energy. And our major activities involve to promote information exchange on exploration, mining, processing of uranium and thorium ores, design, manufacturing, and performance of conventional and advanced nuclear fuels, management of spent fuel, including storage, treatment of spent fuel, and recycling of plutonium, uranium, and monoactinides. And how we do it through the various activities related with the technical cooperation, either in the regional basis or inter-regional basis, and organizing the technical meeting that gives a platform for sharing of some of the information presented on a particular specific activity's objective. We organize a symposium once in a while perhaps once in 4 years. The best example that we organized an international symposium on first reactor and related fuel cycle with CEF technologies in March in 2013 in France, hosted by CEA. Then we have the coordinated research project. That is an important platform. IAEA, the agency, does not carry out any research, but we support research activities of the member states, both developing as well as the developed countries, in the form of coordinated research projects. Then ultimately we come out of this preparation of the technical, state-of-the-art technical documents, which gives this lot of information to help for the distribution of information among the different member states of the agency. And also we maintain, as a part of integrated nuclear fuel cycle and information system, some of the databases on nuclear fuel cycle systems. And these databases are available to all the member states. Only thing one has to register to our agency site. Now, how we do it, we have the 4 group of papers. 4 group which look after uranium group is mainly related with this exploration mining of uranium resources, as well as thorium. The fuel engineering, these activities under this program is mainly related with this, of these various issues related with this, mainly the light water reactor fuel, right from the performance to, and also even the development of the various type of conventional structural materials used in light water reactors. The third one is the spent fuel management. There, we address the activities related with the spent fuel management when it is discharged from these reactors, particularly related with this long-term management of the spent fuel. And the last, the advanced fuel cycle activities, which I am responsible to look after in the agency. What we have, and what is this very objective of this advanced fuel cycle, the way we understand, is to facilitate the development of innovative fuel cycle. What do you mean by the innovative fuel cycle? The fuel cycle which must be economically viable, efficient utilization of both fissile and fertile materials, safe and environmentally friendly, proliferation resistant, at the same time it must be sustainable. So this program that we have under the Advanced Fuel Cycle Program, this various program, the fuel and fuel cycle for water-cooled, thermal, and liquid metal-cooled fast reactors, use option for reprocessed uranium. This is another area, because the spent fuel, which is discharged now from even for light water reactors, contain more than 95% of uranium. And the characteristics of this uranium depends on at what burner it has discharged. So there is a lot of challenges in the use and management of this reprocessed uranium. Then thorium fuel cycle, earlier, there is no activity specific to the thorium fuel cycle. Thorium fuel cycle is a part of the other program. Now, depending on this, in a growing interest of the member states in the area of the utilization of the thorium fuel cycle in various reactors, we have initiated a specific program related to the thorium fuel cycle. Then this, advanced technologies in fuel fabrications. Today's fabrication technology is mainly based on the powder technology. And when we look for the advanced technology, even for the thorium fuel cycle, we have to look for some of the technologies. We have to develop the process technology, which must be amenable to automation and remotization. Then the one important area is partitioning and transportation. This is a very important area because it entirely changes the characteristics of the waste that is to be disposed of. And this is involving either by advanced partitioning methods, involving this advanced aqueous-based processes or the pyro processes, and also this monoactinide bearing fuels and tigers using particularly in the fast neutron energy spectrum. Then fuel and fuel cycles for the high-temperature reactors. We also see there is a revival of interest of the high-temperature gas-cooled reactors, based on using. So there are, what are the current issues and the future perspectives involved in the development of this type of fuels and use it high-temperature gas-cooled reactors and fuel cycle options for SMOs, small and medium-range reactors, particularly with the long core life. Long core life, is of the order of 30 years. So if you see that the way this I understand the thorium, That's major incentives that I have just listed down, what is the natural abundance of thorium research is, of course, that we do have this, as you all say, that 3 to 4%, 3 to 4 times more than this. Then thorium-232 is a better fissile material than, and produces the best fissile materials. As you know, this from the neutron absorption cost, it is almost the 3 times more for the thorium-232 to absorb neutron compared to this uranium-232. Then improved thermophysical properties. Yes, it has a high melting point. It has a high thermal conductivity. It is almost of the order of 30 to 35% higher than the uranium oxide. Low coefficient of thermal expansions. And because of this, one can expect a better fuel performance because this fuel, with thorium-based fuel, is much cooler in nature compared to this uranium and plutonium fuel in water-cooled reactors even under the same operating conditions. And as a result, your fission gas releases, swelling reduces drastically because these are basically a function of temperature. Then suitability, high conversion ratio fuel cycles. As already mentioned, it has a potential that we can have a sustainable thorium fuel cycle in water, even in the thermal reactors. Then thorium-based fuels have intrinsic proliferation rates. This is because of this presence of uranium-238. The amount of 238 depends on where it is used, based on the neutron energy spectrum and also the irradiation time and the low radiotoxic waste. So that is because from the monoactinide point of view. So what are the challenges? We do have the challenges because thorium and thorium-based mixed oxide, unlike EO2, do not dissolve easily in concentrated nitric acid. It is such a stable material, thorium oxide. It is one of the thermodynamically stable material, and in fact, it does not react with many of the structural materials even. The automated and remote operation is well-served facility for thorium-232 and U-233 fuel fabrication. Fuel fabrication is the challenging one. 3-stream processes of separation uranium, plutonium, thorium from spent thorium plutonium oxide fuel is yet to be developed. And the more important challenge is that we do have, as in today, the limited database and experience of thorium fuels and thorium fuels compared to uranium and uranium plutonium fuels. But whatever I have shown, this advantage or challenges, these are basically based on the physical properties and thermophysical properties of material that did exist in 60s, that do exist in today even. However, the challenges has been reduced to a much extent because of the technological development for this over the few decades. So, if you see that, yes, thorium has been utilized in a large scale in both experimental and power reactors. What I want to see that, if you see that there's a various type of reactors where thorium has been used in different form of others, right from the water-cooled reactors, high-temperature reactors, molten salt reactors, fast reactors, etc. This gives some idea about how much of thorium has been used in different type of reactors like Dragon in the United Kingdom, AVR in Germany, Pitch-Bottom, USA, thorium high-temperature reactor, Germany, and Fortson reactors in USA. Among of these, most of the although the experimenter, this THTR and this Fortson USA is a power reactor generated electricity in the range of 300 megawatt reactor. Then why this thing has dropped? Because of this, because if you see the past and present, that between 1960s and mid-80s, there was a lot of development was taking place on thorium fuels for various reactor systems. However, the motivation for the near-term deployment of the thorium utilization dropped due to 2 reasons. One is the low uranium price at that time. At the same time, the weak sentiment towards nuclear power in several parts of the country, except the countries like India, where the R&D on thorium fuel development was going on. So now what has changed? Because whatever the challenges, whatever the incentives did exist in 60s, do exist in today, then what has changed today? Why the interest of this is growing? Today, the perception of looking at nuclear energy has changed. We do not want a clean source of energy just as a source of energy. We want nuclear energy as a source of energy for this, so that the energy can be sustained on a long-term basis. So when we say the sustainable development of nuclear energy on long-term basis, with CEP technology in particular, then just the resources is not the only issue, it is one of the issues. We have to address some of the issues, particularly the issues, apart from this efficient utilization of resources, because thorium, we know that there is a large potential of thorium resources. Apart from this, we have to address the issues like transuranic actinide, particularly the plutonium monoactinide management, because this changes entirely the characteristics of the waste. As you see that, if you remove the spent fuel from uranium and plutonium, then this radioactivity is dictated by the presence of the monoactinide. Today, the technology is well developed, even to contain the waste through the partitioning and conditioning. But still, it is, this radiotoxicity dictated by is something to do with the public perceptions, because it takes thousands of years to come down to a natural radioactive radioactivity. So if we can separate these monoactinides, along with uranium and plutonium, then we know it is dictated by only the fission products, and most of the fission product half-life is 30 years, and if you take this almost 10 half-life, it takes around 300 to 400 years to come down to the negative, so that what we say that institutional control period for the waste management reduces to the level of 300 years. So that perhaps will change the perceptions of the public mind for the acceptance of the nuclear energy for this thing. And then one has to ensure that there is no proliferation. One has to ensure there is no unauthorized diversion for non-peaceful purposes, that for these fissile materials. So all these issues are well addressed by the thorium fuel cycle for the sustainable development. That is the reason why we'll see in the days today, or even the days ahead, that there is a growing interest for the utilization of thorium fuel cycle. So we have organized a lot of technical meetings in the recent times, particularly on the area of world thorium resources, was held in Sweden in October, but this is just related with thorium resources. Then fuel integrated during normal operating accident conditions. Many of the papers related with the thorium fuel, particularly the performance modeling under accident conditions, were presented in this meeting. Then advanced fuel cycle in phase W, again thorium-based fuels as an advanced fuel for use in phase W has been presented in this meeting. Then thorium resources and provinces was sent recently in Vienna, but again it is regarding the different resources and provinces for the thorium deposits. Now we have initiated a coordinated research program titled, we gave this near-term and promising long-term options for the deployment of thorium-based nuclear energy. And this ERP provides a platform for sharing of research gadgets, and the key focus of this, the development strategies for the deployment of thorium on near, medium, and long-term frames, and identification of the gaps in achieving the same. The research objectives that we have fixed for this research program, that we look for the different reactor systems from the view for a concept design that can be effectively used thorium as a fuel, then thorium-based fuel fabrication and processing technologies, thorium fuel performance, spent fuel reprocessing technologies, economics of thorium fuels, then the identification of gas that may affect commercial deployment, strategies for deploying thorium fuel cycles in different time frames. We received almost 12 proposals in the form of research contract as well as the research agreement from the different member states. We accepted out of this the 9 proposals, and the participant countries are Canada, China, Czech Republic, Germany, Italy, Israel, India, Russian Federation, and USA, and to more or less cover the whole spectrum of the reactor system, light water reactors, gas-cooled reactors, molten salt reactors, etc. So if I go one by one, this is what we received. The Westinghouse of the United States is looking after this investigation of performance of thorium-based fuel cycles in PW, first reactor multi-type system. Their main objective to use the use of thorium for transuranic waste burning in a multi-type reactor system. This work aims at addressing the suitability and potential advantages for thorium-based nuclear system to perform full actinide recycle with transuranic isotopic burning. The system comprises the current PWRs, reduced moderation water reactors, and also the liquid moderate fast reactors. So preliminary neutronic analysis shows that thorium enables sustained transuranium bonding in all reactor system analyzed, reduced moderate power reactor, the specialized water reactors, boiling water reactors, as well as the fast reactors. Then we have this, this Institute of Nuclear Engineering Technology of Tsinghua University, China. They are mainly working in the area of the high-temperature gas-cooled reactors. They have a HTR10, using this coated particle fuels in the form of pebble bed, and they are in the process of constructing a HTR-PM, which is of the order of 200 megawatt reactor. Will be these coated particles they are using with the CO2 as a fuel, enriched CO2 as fuel. However, they are investigating the feasibility of utilizing thermal fissile building capability of thorium to the fuel cycle in these things. So analysis of neutronics feature of this fuel cycle in equilibrium state of, this is what they have undertaken this. So they reported that the investigation indicates that thorium U2-3 fuel cycle in STM fuels is feasible and realistic. Now we have this Nuclear Research Institute from Czech Republic. They are looking after, the institute is working on the molten salt reactors. They are looking to the various R&D aspects necessary for the future development of thorium in molten salt reactors. And they are in the MSL reactor physics, neutronic studies, and the experimental development of fluoride biochemical separation processes devoted to particularly the molten salt reactor thorium uranium fuel cycle. Then these Atomic Energy of Canada Limited, Canada, they are investigating on thorium fuel cycle in CANDU as a part of this, and they encode this fabrication technology, radiation testing, postage, metal process as well. So as a first step, they have taken this project, this fluoride polarity as a method to separate uranium from used thorium-based fuel. What they have done is they have separated some small experimental facility where they have taken this thorium uranium fuel and simulated irradiated fuel, and they are doing this thermochemical behavior using this thermodynamic modeling to understand that this thermochemical behavior of thorium, uranium, oxygen, and fluorine system at various temperatures. And this software will be used to predict the stable equilibrium chemical species present at a given experimental conditions so that the process parameter can be optimized. Then we have from Israel the investigation of possibility. That is the area of this redox experiment reactors that from Israel, and the research work involves that, and this is taken by one of the students of, I understand he is the last PhD student of Professor Radowski, is working in this area of these things. The research work involves this, design of PWR and BWR system with a self-sustaining thorium fuel cycle and outlining the main design challenges. Among the challenges, the basic trade-off between the achievable power density and building performance is a key issue. That what he has said that he done is the one of the project constraint is that yes, what is the LW design he is considering should have this conventional reactivity control means so that it can be potentially retrofittable into the current generation of light water reactors. Then we have, of course, this investigation of near-term utilization of thorium in heavy water reactors at Bhabha Atomic Research Center in India. And this work includes these concepts of utilization of thorium in heavy water reactors, including the comparison of different fuel cycles that could be adopted for this reactor system, then analytical and experimental activities of thorium plutonium, MOX, thorium low-enriched uranium MOX type fuels in the area of fabrication, performance modeling, out-of-pipe properties evaluation, and in-pipe irradiation and PIE. The studies of open fuel cycles such as spent fuel behavior during extended storage, characterization of spent fuel for waste management is also the part of their program. Then this, Politecnico di Milano, Italy, they are investigating their nuclear science engineering department of this institute is investigating the thorium fuel fast reactors from the viewpoint of waste management and coal safety features. So that they have considered three types of fast reactors for this study. One is trans-uranium, this burner sodium cooled fast reactor, that is what is called as an actinide recycling reactor. Then isobutane red cooled reactor, that is European red system. Then the first reactor, molten salt reactor. So they are studying this, all these, they've taken this, all these type of fast reactors for their studies. Then we have, this thorium has been extensively used in high-temperature reactors, particularly in Germany, as in Spain, the AVO, as well as THGR. So we have fortunate to have one of the experts who were, involved right from the beginning of the development of the HTGR in Germany, who has gone through this designing for fuel manufacturing, performance modeling, performance analysis under transient and even accident conditions. So there are a lot of information available which are not been reported or not documented. So we have taken this opportunity under this coordinated research project to engage him to, to collect all the informations and ultimately compile in the form of document, which will give these entire informations of the thorium-based fuel performance, particularly the thorium uranium oxide, and also the carbide performance of this type of fuel. These things, we have received this document and we have the plan to publish it as a separate document apart from the final report of this coordinated research project. Then we have this another institute in Germany that is, what is called the Helmholtz Zentrum Dresden Rosendorf. I think the person from Germany will understand better. So they have taken the steady state and accident analysis of 100% thorium oxide PWR core. Then 100% thorium mixed oxide PWR core behavior under steady state and accident conditions will be compared with that of typical uranium fuel pressurized water reactor and 100% MOX pressurized water reactor cores. Then finally they will conclude regarding the neutronic feasibility of 100% of this thorium oxide PWR core. Just a few seconds. Then we have this Institute of Power Engineering, Physics and Power Engineering from Russian Federation. So they are basically looking into this, the elaboration of light water reactor concept for thorium uranium fuel cycle. They have just recently participated in this, that we have recently received these proposals from this and these things, and that is the selection of the principal dimensions for the reactor and preliminary determination of the fertile and fissile material content in the supercritical core, taking into account the parameters such as fuel rods, fuel assemblies, control rods, blankets, coolant flow rates, and its thermal properties, etc. The choice has to be based on condition of maximum bleeding. And then determination of basic fuel characteristics, namely initial charge of fissile and fertile materials, annual charge, and discharge with calculation of isotopic vectors, and determination of fresh and spent fuel radiotoxicity. Then we have initiated the new CRP. The CRPs are normally for the period of 3 years. The last CRP that we initiated last year is for 20, but however, depending on the progress of work, the period can be extended further. So we have instituted a new CRP that is on the reliability of high power, extended burn-up, and advanced PHWR. Thorium fuels is a part of it. It's not exclusively for the thorium fuels. The reason for taking the CRP, that similar project has been taken for the light water reactors. But if you see this light water reactor fuels design and these PHWR fuel designs are entirely different. Their operating conditions are entirely different. You have a short fuel fin, collapsible core, clad, no space for accommodating the no plenum space, and also this fuel is operating at a high heat rating. So all these conditions and this going for the high burner is a very challenging particularly for the pressurized heavy water reactors. So what we have done, because of this, there are certain performance issues coming out because of increased release of gaseous and volatile fission product, plate-clad interaction, degradation of fuel properties, burn-up dependent thermomechanical properties, gas coefficient. So the research topic we have specific in mind, that is the fuel concepts for high burn-up, particularly the design, material, and fabrication, life-limiting aspect of the extended burn-up, and advanced fuels, including accident-tolerant fuel, and advanced fuels leading to improved safety margin. So these are some of the old and recent publications on the specific to the thorium fuels, as well as some publications where thorium fuels, a few chapters are devoted to thorium fuels. This is done by the role of thorium to supplement fuel. These are very recent publications, and these are some of the old publications available for this utilization of this. just so documents. We are also in the process of publishing a document on world thorium resources. We already have the thorium depot, just similar to the uranium depot. It just gives, as a part of integrated nuclear fuel cycle system, it just gives the information about the resources, but it doesn't give any details. So we are coming out with a document on this. These are the contributors from the various member states, and these are the major source of informations for this draft document. Draft documents is already under preparation, and hopefully this document will be published in next year. So in summaries, we say that use of thorium-based fuels has demonstrated in almost all type of reactors during the period 1960s to this. Large resources thorium, along with favorable waste management and intrinsic proliferation of thorium-uranium fuel cycle, has the potential for the sustainable development of nuclear energy. Technological challenges for remote and automated processes, even for the front end of thorium fuel cycle in well-sheltered facilities, this stay there. And most important, that the global attitude towards deployment thorium are fast changing. And the best example is today's conference, the more than 200 participants from 32 countries. So I hope that with this interest, first changing in the interest, days are not far off that we see the near-term deployment of the thorium fuel cycles in various types of reactors. Thank you very much for your time.
Thank you, Dr. Basak. Again, since we are already behind time, we'll have time for one question if there is. Anybody asking question? Yeah. Can I get the mic here?
I wonder about the official position of the international agency on the concerning accelerator-driven systems, especially energy amplifier.
This acceleration-driven system is not a part of this, what of the program. This is taken by this other group in the agency. But there, as far as I know, there is some activities, existing in the area of this ADS.
Okay. With this, we return our thanks to Dr. Basak. Thank you very much.